topologically speaking, a human being is essentially a donut.
Right, which is always a weird thought.
It really is.
Yeah.
But think about it. From your mouth all the way down to the end of your digestive tract, there is just one continuous hollow tube running directly through the center of your body.
At a single pipe.
Exactly. Which means that when you eat something, say, like a massive, complex, protein-heavy cheeseburger, and you swallow it, that burger hasn't actually entered your body yet.
No.
It is still in the external environment, just passing through the hole in the donut.
It's a profound shift in perspective, you know, when you realize that the food inside your gut is technically outside your internal environment.
Right.
Because we spend an immense amount of cognitive energy planning what we eat, analyzing macros, savoring flavors. But the moment that food slips past the back of your throat...
You're just along for the ride.
Completely.
Yeah.
Conscious control ends, and this automated industrial complex just takes over.
And we want to take you on a journey through that exact complex today. This is our deep dive into the gastrointestinal tract.
The GIT.
Yeah, the GIT. We have a really dense stack of physiological research, anatomical diagrams, clinical notes, and our goal today is to reverse engineer the whole thing.
We're going to look at the muscular pacemakers, the massive fluid shifts, the chemical solvents, and the localized second brain that manages this entire disassembly line.
And it does all of that without ever bothering your conscious mind.
Thankfully. So to map the territory first, the source material divides the digestive system into two distinct categories.
Okay.
First, there is the primary alimentary canal, the gastrointestinal tract itself. That's the continuous muscular... It encompasses the mouth, the pharynx, the esophagus, the stomach, the small intestine, and finally the large intestine, ending at the rectum.
So that's the main conveyor belt.
Exactly, the conveyor belt. But a conveyor belt alone can't dismantle a complex meal. So the second category consists of the accessory digestive organs.
Like the support staff.
Yeah. These are the glandular structures located completely outside the main tube, but they dump vital chemical supplies into it.
So we're talking about what? The salivary glands?
Salivary glands, the exocrine pancreas, the liver, and the gallbladder. The food never actually enters these accessory organs.
Okay, right.
But without their continuous chemical injections, the entire disassembly line would just grind to a halt.
So if we treat this gut like a sophisticated factory floor, you know, the raw materials arrive at the loading dock of the mouth. They get pushed down the line, smashed apart by heavy machinery, bathed in specialized industrial solvents, and then the valuable components are extracted and shipped into the bloodstream.
Right. And whatever is left over just gets compacted and shipped out the back door.
Perfect. So before we zoom in on the specific cellular machinery running that factory, the physiological texts establish 4 fundamental processes.
Yeah, these govern everything happening inside the tube. Every single function falls under one of these 4 pillars.
And those are motility, secretion, digestion, and absorption, right?
Yes. Plus a 5th one, excretion, to finish it off.
Right. So let's define the parameters of each. Motility is basically the physical energy of the system.
It's the muscular contraction.
Yeah, mixing the contents and propelling them forward. It is the literal physical force applied to the raw materials.
Because without motility, the system is totally stagnant. Nothing happens.
Right.
Next up is secretion. As those materials are moved along, exocrine glands lining the tract pump digestive juices directly into the lumen.
And the lumen is just the hollow space inside the tube, right?
Exactly. And these secretions are complex mixtures. They're water, electrolytes, and highly specific organic constituents.
Like enzymes and stuff.
Yeah, enzymes, bile salts, and protective mucus.
Okay, so we have movement and we have chemical baths. That leads to the 3rd pillar, which is digestion.
The main event.
Right. The notes define this as the actual breakdown of large food particles. You take a complex carbohydrate and break it into simple sugars like glucose.
Or a massive protein chain down into individual amino acids.
Yeah, or taking dietary fats and breaking them into fatty acids. Yeah. And all of this is accomplished through a combination of mechanical shearing from the motility
right, the somatic,
and enzymatic hydrolysis from the secretions.
Which leaves us with the ultimate goal of the entire operation, right? Absorption.
Right.
Once the physical and chemical breakdown is complete, those simple microscopic units plus water and electrolytes are actively transported out of the lumen.
They get pulled across the epithelial cells lining the gut and then deposited into the blood and lymphatic vessels. I want to pause on digestion versus absorption for a second, actually.
Sure.
Because in casual conversation, People blur these together constantly.
All the time.
Right. Someone eats a massive Thanksgiving dinner, collapses on the couch, and says, "Give me a minute, I'm digesting."
When they usually just mean their body's absorbing the meal.
Exactly.
Right.
But if we really looked at the biology, digestion and absorption are fundamentally different events.
Right. They are completely distinct physiological events. Digestion is polymer depolymerization.
Okay, big words.
Basically, it's the act of taking a complex architectural structure, like a Lego castle, and breaking the chemical bonds holding it together.
So breaking it into individual Lego bricks.
Yes. Whereas absorption is the act of physical relocation across a biological barrier, putting the bricks in your pocket.
So if I eat a piece of steak, digestion is the chemical act of severing the peptide bonds between the amino acids that make up the muscle fibers of that cow.
Exactly.
But even after those bonds are severed, those free-floating amino acids are still sitting inside the hollow tube of my gut.
Still technically outside your body.
Right. Absorption is the act of grabbing those individual amino acids, pulling them through the wall of the intestine, and dropping them into my bloodstream so my own cells can use them.
That is the crucial threshold right there.
Wow.
Digestion breaks the structural integrity. Absorption crosses the physical border.
Okay, that makes sense.
And what the source material really emphasizes is the absolute interdependence of these processes. You can't just absorb a complex protein molecule.
It's just physically too large. Right.
Right. It's too big to pass through the enterocytes, the intestinal absorbing cells, so it must be digested first.
But then effective digestion requires the heavy mechanical churning of motility to increase the surface area.
Yeah, and the massive influx of enzymatic fluids from secretion.
So it's all connected. And the notes add a fifth term to complete the cycle: excretion.
Right. Whatever cannot be digested or simply isn't absorbed is eliminated as feces through defecation. It's the factory's waste protocol.
So now that we have the parameters, we really need to look at how the physical machinery operates.
The motility.
Yeah. If motility is the prerequisite for moving and mixing the food, we have to ask how the gut actually coordinates this movement without any conscious input from the central nervous system.
Because, unless someone is practicing a highly obscure internal martial art, no one is consciously flexing their intestines to move their lunch along.
Right, I'm certainly not. This entire muscular operation is running on autopilot.
Completely. And our sources outline two distinct categories of this movement: propulsive movements and mixing movements.
Let's start with propulsion, specifically peristalsis. How does a hollow tube push something forward automatically?
Well, peristalsis is an involuntary reflex response, and it's primarily driven by the smooth muscle lining the gastrointestinal tract.
Okay.
The trigger is actually mechanical. When a bolus of food enters a section of the gut, its physical volume stretches the muscular wall outward.
So the physical pressure of the food is literally the switch that turns the muscle on.
Yes. And the response is incredibly elegant. The mechanotransduction triggers a circular contraction in the muscle layer located immediately behind the stretched area.
Behind the food.
Right. And simultaneously, the neural circuitry triggers a relaxation of the muscle immediately in front of the food bolus.
Oh, wow. So you have a high-pressure zone behind the food and a low-pressure receptive zone ahead of it.
Exactly. This wave of contraction then sweeps in an oral to caudal direction from mouth to tail.
It's exactly like the classic toothpaste tube mechanism.
Yeah, that's a perfect analogy.
If you want to move toothpaste forward, you don't squeeze the middle of the tube. You pinch it shut at the back, and the open space in front provides the path of least resistance.
You just roll that high-pressure pinch all the way down.
Right. But peristalsis alone is inadequate for digestion, isn't it?
Yeah, it is. Because if the gut simply pushed food rapidly from one end to the other, the enzymes would only interact with the superficial outer layer of the food bolus.
The interior of the mass would remain totally untouched and undigested.
Which is why we need the second type of motility: mixing movements, specifically what the notes call segmental contractions.
Okay, so how do those work?
Well, mixing movements serve two vital functions. First, they aggressively fold the food into the digestive enzymes, accelerating chemical breakdown.
Right.
Second, they force the newly broken down molecules against the absorptive surfaces of the gut wall.
So it's not just about pushing it down, it's about rubbing it against the wall.
Exactly. To achieve this, the smooth muscle shifts from a sweeping wave to a localized, alternating pattern of ring-like contractions.
Like kneading dough.
Yeah. Imagine a long, fluid-filled balloon. If you squeeze it simultaneously in several distinct spots, the fluid bulges out into the relaxed spaces between your fingers.
Uh-huh.
A few seconds later, you release your grip and squeeze those exact bulging areas instead.
So you are constantly forcing the contents back and forth into alternating compartments. It's not really moving forward, it's just being kneaded and sloshed around in place.
It creates immense shear force. This mechanical agitation physically breaks down larger lipid droplets and ensures that every single molecule of food is repeatedly brought into contact with the mucosal lining.
Where the absorption actually takes place.
Right.
But this raises a massive mechanical question for me. We've got sweeping toothpaste contractions, and we've got alternating localized compressions.
Yeah.
Who is keeping time? Skeletal muscle contracts because a nerve from my brain tells it to. But this smooth muscle is operating independently. What is generating the rhythm of the gut?
This is where we encounter one of the most fascinating microstructures in human physiology. Embedded within the muscle layers of the gut are these specialized pacemakers.
Okay.
They're known as the interstitial cells of Cajal.
The interstitial cells of Cajal. They sound like a hidden guild running the factory floor.
They essentially are. These are specialized, star-shaped cells located in the interstitial spaces between the longitudinal and circular smooth muscle layers.
Right.
The most critical thing to understand about these cells is that they are non-contractile.
Meaning they don't flex themselves.
Exactly. They do not generate physical force. Instead, their cellular membranes are in a state of constant, rhythmic electrical flux.
Generating what the notes call slow wave potentials, right? The basic electrical rhythm.
Yes.
I want to dig into the biochemistry of this because the notes are very specific. These slow waves are spontaneous, undulating changes in the electrical charge across the cell membrane.
Driven by the rhythmic, fluctuating activity of the sodium-potassium pumps.
Right. But the massive bold print caveat here is that a slow wave is not an action potential.
And that distinction is the key to the entire regulatory system. In cellular physiology, an action potential is the all-or-nothing electrical explosion that commands a muscle fiber to contract.
Right, it's the spark.
Yeah, and in smooth muscle, that contraction is driven primarily by the influx of extracellular calcium ions. But a slow wave does not open those voltage-gated calcium channels.
Then it doesn't let the calcium in.
Nope. Therefore, a slow wave by itself produces zero muscular contraction.
So what are they actually doing if they aren't causing contractions?
They are continuously bringing the resting membrane potential closer to the threshold of firing and then letting it drop back down. It's an oscillating baseline.
Oh, I see. It's like a drum major leading a marching band.
How so?
Well, the interstitial cells of Cajal are the drum major, constantly tapping a steady, unrelenting tempo on a snare drum. Tick, 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 tick. That steady rhythm is the slow wave.
Okay, I like that.
It's always humming in the background of the gut. But the band isn't playing any music yet. The brass section isn't blowing their horns. The drum major is just maintaining the tempo.
Right.
The actual music, the forceful, calcium-driven muscular contraction,
right,
only happens if a specific cue is given.
Exactly. The slow waves essentially raise the baton, priming the system, but they stop just short of the threshold required to initiate the physical work.
So what is the cue that pushes the system over the edge?
It comes back to the presence of the raw materials.
The food.
Yes. When food enters a specific segment of the tract, the physical stretch of the muscle wall, combined with localized neural and hormonal signals, causes the entire baseline electrical charge to shift upward.
It depolarizes the resting membrane potential.
Exactly.
So the drum major is still tapping the exact same rhythm, but the whole baseline of the band has been elevated.
And because that baseline is elevated, the peak of the next slow wave suddenly breaches the critical threshold voltage. The moment that threshold is crossed, true action potentials fire. Voltage-gated calcium channels fly open, calcium floods into the smooth muscle fiber.
And binds to a protein called calmodulin, right?
You got it. And that initiates the cross-bridge cycling that physically shortens the muscle.
And the beauty of this is that the action potentials, the horn blasts from the band, only happen at the peak of the drum major's beat.
Perfectly synced.
The muscle doesn't just spasm chaotically when food arrives. It contracts perfectly in time with the underlying slow-wave rhythm set by the interstitial cells of Cajal.
The graph provided in the source material visualizes this flawlessly. You see a gentle sine wave undulating below a dotted threshold line.
Right.
When the tissue is empty, the wave just rolls on, burning very little energy. But when stretch is applied, the entire sine wave shifts upward along the y-axis.
And then the peaks pierce the threshold.
Exactly. And exactly at those peaks, you see a rapid burst of sharp vertical spikes. Those are the action potentials. And immediately following those bursts, the secondary graph showing muscle tension spikes upward.
It's an evolutionary masterpiece of energy conservation, really.
It truly is.
The gut remains perfectly synchronized, humming with a baseline electrical readiness. But it only expends the massive ATP required for heavy mechanical churning when there's actual material present to process.
Furthermore, because these pacemaker cells are localized, different regions of the tract can be tuned to completely different baseline frequencies,
Optimizing the motility for that specific organ's function.
Exactly.
Yeah, our sources provide the exact telemetry for these different zones. Like down in the stomach, the pacemakers are humming at a very slow, methodical 3 waves per minute.
Pretty slow.
But the moment you cross the pyloric sphincter into the duodenum, the start of the small intestine, the tempo quadruples to 12 waves per minute.
Right.
Further down in the ileum, it dials back to 9 waves per minute. And by the time you reach the large intestine, the cecum drops to an incredibly sluggish 2 waves per minute. Why the drastic shifts in speed?
Well, form follows function. The stomach is primarily a holding vat and a preliminary mixing chamber. It needs to grind dense, solid food into a liquid paste called chyme.
So a slow, crushing 3 waves per minute allows for massive force generation.
Yes, and thorough mixing with stomach acid. But the duodenum is a critical chemical junction. It's where the highly acidic chyme from the stomach is suddenly bombarded with bicarbonate and potent enzymes from the pancreas.
So it requires rapid, aggressive agitation to instantly neutralize the acid.
Exactly, to initiate chemical breakdown before the delicate intestinal lining is damaged, hence the rapid 12 waves per minute.
It's the highest intensity mixing zone on the factory floor.
And conversely, by the time material reaches the large intestine at 2 waves per minute, the goal is no longer rapid chemical processing.
What's the goal then?
Slow, deliberate fluid reclamation. The material needs to sit in place long enough for the epithelial cells to pull the water back out of the waste.
Okay, so we have the pacemakers setting the local tempo, and the food providing the stretch to trigger the actual contraction. But there's a missing link here.
What's that?
The interstitial cells of Cahal are sparsely distributed. So how does the electrical signal instantly propagate through the thick layers of smooth muscle so that a massive, synchronized ring of tissue contracts all at once?
That is because the smooth muscle cells of the gastrointestinal tract operate as a functional syncytium.
A functional syncytium.
Yes. In most skeletal muscle, every single muscle fiber must be individually innervated by a nerve ending to contract. But in the gut, the smooth muscle cells are physically coupled together by gap junctions.
Let's zoom in on gap junctions because they seem essential for this autonomy.
They are. A gap junction is essentially a highly specialized protein tube that pierces the cell membranes of 2 adjacent cells, locking them together.
Like a little tunnel.
Exactly. These tubes create pathways of extremely low electrical resistance. When an action potential fires in one cell, the positively charged ions don't have to wait for a chemical neurotransmitter to cross a synapse.
Oh, they just flow directly through.
Right. The ions simply flow directly through the gap junction into the neighboring cell, instantly depolarizing it as well.
It's like lighting a trail of gunpowder. The electrical fire sweeps through the entire sheet of muscle instantaneously.
Precisely. The interconnected muscle fibers behave as a single, massive, coordinated unit, a syncytium. If one cell hits threshold, the entire localized region fires.
Wow. And this incredible automated machinery, the pacemakers, the syncytium, the stretch reflexes, it operates entirely via smooth muscle, which is involuntary.
Right.
The notes point out a crucial anatomical boundary here.
Right.
Skeletal, voluntary muscle only exists at the very entry and exit points of the system.
Yeah, we retain voluntary control over the mouth, the pharynx, the upper third of the esophagus, and the external anal sphincter.
We consciously initiate the intake of food through chewing and swallowing, and we consciously control the timing of defecation.
And everything in between the upper esophageal sphincter and the internal anal sphincter is surrendered to the gut's autonomous programming.
Okay, so the conveyor belts are running, we understand the motility. But physical crushing isn't enough to extract nutrients. We need the chemical solvents.
Which brings us to the second physiological pillar, secretion.
Secretion.
Secretion is arguably where the most intense biochemical labor occurs. Throughout the entire length of the tract, highly specialized exocrine glands are continuously manufacturing and pumping massive volumes of digestive juices into the lumen.
And what exactly constitutes a digestive juice? The notes categorize the composition into 3 parts, right?
Yes. First, an overwhelming amount of water. Second, inorganic constituents, which are electrolytes like sodium, chloride, and bicarbonate.
Okay.
And third, organic constituents. These are the heavy hitters.
Like the enzymes that catalyze the breaking of molecular bonds.
Exactly. Plus the bile salts that emulsify giant fat globules into manageable droplets, and the heavy mucus that lubricates the passage and protects the gut wall from digesting itself.
The logistical challenge of secretion is staggering when you look at the volume.
Yeah.
These exocrine cells don't just magically generate this fluid out of nowhere.
They really don't.
Every single drop of water, every sodium ion, every building block for those enzymes must be extracted directly from the blood plasma circulating through the capillaries in the gut wall.
Yes.
I really want to emphasize the sheer scale of this fluid transfer because it sets up what our sources call a clinical bridge. And this concept completely reframed how I view human hydration.
It's fascinating.
To break down a heavy meal, the gut requires an aquatic environment. It has to flood the lumen so the enzymes can physically float around and collide with the food molecules.
Right.
To do this, your exocrine glands literally drain water out of your vascular system.
Yeah.
They are borrowing an ocean of plasma from your blood.
It is a massive physiological investment. You are pulling liters of fluid out of your circulating blood volume and dumping it into an external space, the lumen of the gut.
Wow.
Now, under normal physiological conditions, this isn't an issue because the system operates as a closed recycling loop.
Right.
Once the fluid has facilitated the chemical digestion, the absorptive cells lower down in the small and large intestines pull all that water, along with the newly freed nutrients, right back across the barrier and into the bloodstream.
So the body recoups its investment.
Exactly. But the clinical bridge explores what happens when that recycling loop catastrophically fails.
The notes state, failure to reabsorb digestive secretions because of vomiting or diarrhea leads to loss of these fluids, dehydration, and thus decreases plasma volume and blood pressure.
This is a critical piece of clinical physiology. When a person is suffering from a severe gastrointestinal infection like cholera or even an aggressive rotavirus, the immediate danger is not caloric starvation.
Right. It's not about food at that point.
No. The acute life-threatening danger is profound hypovolemic shock.
Let's trace the logic here because this blew my mind. When you have severe unremitting diarrhea, you aren't just failing to absorb the glass of water you drank an hour ago.
No.
You are actively hemorrhaging the fluid that your body purposefully pumped into the gut to process your last meal. You are bleeding water from your cardiovascular system.
The physiology bears that out entirely. Cholera toxin, for instance, irreversibly activates the chloride channels in the intestinal lining.
Okay.
So the cells constantly pump chloride ions into the lumen. Sodium naturally follows the negative charge, and water naturally follows the sodium via osmosis.
So the gut is tricked into massively hypersecreting fluid from the blood.
Exactly. And the absorptive mechanisms are overwhelmed. The fluid exits the body. As that fluid is lost, the total volume of plasma in the blood vessels plummets.
And when blood volume drops, blood pressure plummets.
Right. The heart tries to compensate by beating faster, but there simply isn't enough fluid to maintain perfusion to the brain and vital organs.
It really underscores that the gut isn't just an isolated digestive tube. It is a high-volume fluid manager intimately tied to cardiovascular stability.
A disruption in the gut's fluid recycling can crash your blood pressure in a matter of hours.
It forces you to respect the immense physiological forces at play just to process a sandwich, you know?
Absolutely.
So we have pacemakers dictating rhythmic contractions, and we have millions of glands actively pulling plasma from the blood to flood the factory floor. The coordination required here is immense.
Very much so.
Because if the stomach glands pump acid before the food arrives, you get an ulcer. If the muscles churn before the enzymes are secreted, the food isn't digested. How is the sequence of these events controlled?
That brings us to the control architecture. The gastrointestinal tract operates under a dual management system.
Okay.
First, a localized, incredibly dense neural network known as the enteric nervous system. And second, an overarching centralized control system provided by the autonomic nervous system.
Let's look at the local management first, the enteric nervous system.
Right.
The notes refer to this as the gut brain, and that is not hyperbole. It contains roughly the same number of neurons as the spinal cord.
It's massive. And it operates through two primary interconnecting networks, or plexuses, embedded directly within the walls of the digestive tract.
The first is the myenteric plexus, also known as Auerbach's plexus.
Location dictates function here. The myenteric plexus is sandwiched right between the longitudinal and circular layers of smooth muscle.
So it's right in the muscle.
Exactly. Because of its strategic location, its primary responsibility is the regulation of motility. It controls the tone of the gut, the intensity of those rhythmic contractions, and the velocity of the peristaltic waves.
So myenteric equals muscle management. Got it. The second network is the submucous plexus, or Meissner's plexus.
Right. This one is located deeper in the wall in the submucosa, which sits right beneath the delicate inner lining of the gut.
And because it is adjacent to the epithelial layer, where the glands are located, the submucous plexus primarily controls local secretion and local blood flow.
It dictates exactly how much glandular fluid is pumped into the lumen at any given moment.
I think the best way to conceptualize these intrinsic nerve plexuses is to picture them as the local branch managers of the factory.
Oh, that's a good way to put it.
They're the foreman walking the floor, monitoring the assembly line second by second. They have the authority to speed up a conveyor belt or order more solvent without ever having to call the CEO at corporate headquarters.
And that autonomy is crucial for efficiency. But the CEO, the central nervous system in the brain and spinal cord, still maintains executive override.
Right.
This connection is established through the extrinsic nerves, specifically the sympathetic and parasympathetic branches of the autonomic nervous system.
And the notes detail 3 specific ways corporate HQ can intervene. First, these extrinsic nerves can bypass the local managers entirely and innervate the smooth muscle and glands directly.
Yes.
Second, they can synapse onto the intrinsic nerve plexuses, basically the CEO calling the local branch manager and ordering a blanket increase in production across the board. And third, they can trigger the release of specific gastrointestinal hormones into the blood.
The overarching tone of these extrinsic signals is generally divided by function. The parasympathetic system, often driven by the vagus nerve, is the rest and digest signal.
So it turns things up.
Exactly. It broadly stimulates motility and increases glandular secretion. Conversely, the sympathetic system is the fight or flight signal.
So if you experience sudden extreme stress,
Sympathetic firing will actively inhibit the intrinsic plexuses, halting motility and shutting down secretion because the body needs to shunt that blood flow to skeletal muscle for immediate survival.
wow, so it just pulls the plug on the gut.
Pretty much. Now, to understand how these managers make decisions, our source breaks down the sensory input. The gut wall is lined with 3 specialized types of receptors.
Okay.
First, chemoreceptors. These taste the chemical composition of the food in the lumen. They know if you ate pure fat or pure protein.
Wow.
Second, mechanoreceptors. These feel the physical tension and stretch in the gut wall, allowing the system to gauge the volume of the meal.
To know how much is in there.
Right. And third, osmoreceptors. These measure the osmolarity, the concentration of solutes, to ensure that massive fluid shift we discussed earlier is perfectly balanced.
And the integration of these sensors creates the reflex arcs that drive digestion. The notes divide these into short reflexes and long reflexes.
Correct.
A short reflex is entirely self-contained within the gut wall. Like a mechanoreceptor detects stretch, sends a signal to the local myenteric plexus, and the plexus immediately commands the local muscle to contract.
The signal never leaves the organ.
The brain is entirely unaware it even happened.
This is the true power of the gut brain. The vast majority of the thousands of microadjustments required to process a meal are handled via short reflexes. It is an incredibly sophisticated, distributed intelligence network.
But long reflexes are required for broader coordination, right?
Yeah. In a long reflex, the sensory signal travels all the way from the gut, up the spinal cord to the brainstem, and the motor command travels back down via the autonomic nerves.
So it actually loops through the brain.
Right. Long reflexes coordinate distinct anatomical regions. For example, the physical act of chewing initiates a long reflex that signals the stomach to begin secreting hydrochloric acid before the food even arrives.
Oh, anticipatory regulation. It's getting ready.
Exactly.
Okay, so we've established the mechanics, the chemistry, and the communication network.
Right.
Now, we're going to synthesize all of this.
Let's do it.
We're going to follow the chronological journey of our hypothetical cheeseburger, stop by stop, and examine the precise physiological protocols executed at each station.
This is where we really see the exquisite division of labor, because the alimentary canal is not a uniform pipe. It is a series of highly specialized bioreactors, each with a distinct chemical environment and motility pattern.
Let's initiate the process then. The mouth. The physiological journey begins with sensory analysis taste to ensure the raw material is viable and not toxic.
Right.
Then mechanical breakdown begins with mastication, or chewing.
Mastication is vital not just for swallowing, but for chemical efficiency. By crushing a solid block of food into smaller fragments, you exponentially increase the surface area to volume ratio.
Because digestive enzymes can only act on the surface of a food particle.
Right. If you don't chew thoroughly, you drastically limit the operational surface area for the enzymes downstream.
And those enzymes are introduced immediately via salivary secretion.
Yes.
Saliva is packed with salivary amylase, which begins severing the complex carbohydrate chains of the burger bun, and salivary lipase, which begins attacking the lipids in the cheese.
It starts right away.
But here is a massive detail from the notes that upends normal assumptions. We tend to think absorption only happens deep in the intestines. But the notes explicitly state that the mouth is capable of absorption, specifically highlighting sublingual nitroglycerin.
It's a brilliant pharmacological hack, honestly.
How's it work?
Well, the mucosal lining beneath the tongue, the sublingual region, is extremely thin and supported by a dense capillary bed. While a large protein or carbohydrate cannot cross this barrier, highly lipid-soluble, low molecular weight molecules can diffuse directly across the membrane.
And just go straight into the venous circulation in a matter of seconds.
Exactly.
Which is why someone experiencing angina chest pain from restricted cardiac blood flow places a nitroglycerin tablet under their tongue.
Right. It dissolves, crosses the sublingual membrane, and immediately enters the systemic circulation to dilate the blood vessels.
If they swallowed that tablet, it would have to brave the stomach acid and navigate the entire intestinal absorption process.
Which takes far too long when the heart muscle is starving for oxygen.
It entirely bypasses the gastrointestinal transit time and the hepatic first-pass metabolism in the liver.
Yep. So once the mouth has prepared the bolus, the voluntary act of swallowing, or deglutition, hands the material off to the esophagus.
Now, the esophagus is the most straightforward organ in the system. Its sole physiological function is rapid transport from the pharynx to the stomach.
It utilizes strong peristaltic waves to push the bolus downward.
And it secretes a heavy mucus solely for lubrication and protection against physical abrasion.
But the notes emphasize a critical negative here. Absolutely, NO digestion and NO absorption take place in the esophagus.
It is simply a transit corridor.
That's all. The transit time for a solid bolus is roughly 5 to 8 seconds, ending with the relaxation of the lower esophageal sphincter, allowing the food to drop into the stomach.
Okay, the stomach is where the environment becomes hostile.
Very hostile.
If we look at its motor functions, the stomach acts as a massive storage vat. The upper portion relaxes to accommodate the volume of the meal.
And the lower portion, the antrum, utilizes those slow 3 wave per minute peristaltic contractions to ruthlessly pulverize the food against the closed pyloric sphincter,
turning the solid burger into the liquid slurry called chyme.
But the secretory functions of the stomach are its defining characteristic. The gastric pits lining the stomach wall function as both exocrine and endocrine glands.
So on the endocrine side, specific G cells secrete the hormone gastrin directly into the bloodstream, which acts as a master regulator, stimulating acid production and gastromotility.
Yes. And on the exocrine side, we have the production of hydrochloric acid, or HCl, by the parietal cells.
This acid is so potent it can drop the pH of the stomach down to 1.5.
It is acidic enough to dissolve razor blades.
That's insane. How does a biological cell manufacture industrial-grade acid without immediately destroying itself?
The mechanism is a masterpiece of cellular engineering. The parietal cell doesn't just create a pool of HCl internally.
No, it doesn't.
No, it manufactures the components separately. It uses an enzyme called carbonic anhydrase to generate hydrogen ions, and it actively pumps these protons across the apical membrane into the lumen,
trading them for potassium ions using a massive ATP-driven proton pump.
Exactly. And simultaneously, it transports chloride ions from the blood across the cell and out into the lumen through specific channels.
Ah. So the hydrogen and chloride only meet and combine into highly corrosive HCl once they are safely outside the cell, in the lumen.
Precisely. And to prevent that acid from digesting the actual stomach wall, specialized cells secrete a thick alkaline mucus layer. It's a physical and chemical barrier.
Because the acid destroys the bacteria in the food, and it denatures the complex 3D structures of the proteins, unfolding them so the digestive enzymes can get to work.
Specifically, the chief cells in the stomach secrete an inactive precursor enzyme called pepsinogen. When pepsinogen encounters the severe acidic environment, it physically alters its shape, cleaving off a masking sequence to become the active enzyme pepsin.
And pepsin then begins aggressively cleaving the unfolded proteins into smaller peptide chains.
Right.
So we have massive mechanical crushing and highly corrosive protein digestion.
Uh-huh.
But what about absorption? Again, the stomach throws a curveball.
It does.
The notes explicitly state the stomach absorbs practically zero nutrients. None of the protein or carbs from the burger cross the barrier here. But the stomach does absorb water, alcohol, and aspirin.
And this anomaly is driven by basic chemistry. The stomach lining is heavily guarded by tight junctions between the cells to prevent acid leakage, making it impervious to water-soluble nutrients.
But lipid-soluble substances can diffuse straight through the lipid bilayer of the cell membranes.
Exactly. Ethanol alcohol is somewhat lipid-soluble, allowing a portion of it to be absorbed immediately through the stomach wall into the blood.
Which perfectly explains the mechanics of drinking on an empty stomach.
Yeah, the alcohol doesn't have to wait for gastric emptying to reach the intestines. It diffuses right through the gastric mucosa, hitting the bloodstream rapidly.
And aspirin functions similarly, right?
It does. In the highly acidic environment of the stomach, aspirin molecules remain unionized, meaning they are uncharged and highly lipid-soluble, allowing them to rapidly cross the epithelial barrier.
However, this is also why chronic aspirin use can damage the gastric lining as it accumulates inside the mucosal cells.
True. Now, once the stomach has sufficiently liquefied the meal and initiated protein breakdown, it carefully meters the highly acidic chyme through the pyloric sphincter.
And into the main event, the small intestine.
If the digestive tract is a factory, the small intestine is the vast, sprawling, high-tech extraction facility where the true purpose of the system is realized.
The source material unequivocally states this is the primary site where most digestion and absorption take place.
Let's look at the motor function first. We mentioned earlier that the small intestine uses a combination of propulsive peristalsis to slowly move things along and aggressive segmenting mixing contractions to maximize contact time.
But the secretory environment here is entirely different from the stomach. The acidic chyme must be immediately neutralized, or the delicate intestinal tissue will be destroyed.
And this relies heavily on the accessory organs we discussed at the very beginning. As chyme enters the duodenum, it triggers the release of hormones that command the pancreas to dump a massive volume of bicarbonate-rich fluid into the intestine, instantly neutralizing the stomach acid.
And the pancreas also secretes a cocktail of powerful enzymes, lipases for fats, amylases for carbs, and proteases for proteins.
Simultaneously, the liver and gallbladder inject bile, which acts like biological dish soap,
emulsifying giant insoluble fat globs into microscopic droplets, vastly increasing the surface area for the lipases to work.
The intestine itself secretes succus entericus, an aqueous salt and mucus solution that provides the fluid medium for all this chemistry.
But the final act of digestion in the small intestine doesn't happen floating out in the middle of the fluid, does it?
No, it happens right on the surface of the gut wall, utilizing intracellular enzymes.
The epithelial cells lining the small intestine, the enterocytes, have specialized enzymes literally embedded in their cellular membranes.
These are called brush border enzymes,
including disaccharidases, which break complex sugars down into single glucose or fructose molecules, and aminopeptidases, which snap the final peptide bonds to release individual amino acids.
The final chemical cleavage happens milliseconds before the molecule is absorbed.
Which brings us to the absorption architecture. The biological engineering of the small intestine is obsessed with one singular goal: maximizing surface area.
Because if the inside of the small intestine were a perfectly smooth, flat tube, we would starve to death. There simply wouldn't be enough physical space for the nutrient transport channels.
To solve this, the inner lining is folded into massive circular ridges.
But it goes deeper. The surface of those ridges is covered in millions of microscopic, finger-like projections called villi, which project out into the fluid.
It looks like the texture of a plush velvet carpet.
And it scales down even further. The individual epithelial cells covering each of those villi have their own microscopic, hair-like projections extending from their apical membranes, called microvilli.
That's the brush border.
Yes. By folding the tissue, projecting the villi, and sprouting the microvilli, the small intestine increases its total absorptive surface area roughly 600 times.
Creating a surface area equivalent to the size of a tennis court packed inside your abdomen.
Which is wild.
Every single amino acid, every single glucose molecule, and every single fatty acid from that cheeseburger is actively pulled across that massive velvet-like membrane.
Transported through the enterocyte and dumped into the dense capillary beds and lymphatic vessels hidden inside each microscopic villus.
The efficiency is staggering.
The active transport mechanisms, often utilizing the sodium concentration gradient established by the sodium-potassium pumps on the basolateral side of the cells, ensure that virtually all usable nutrients and the vast majority of the secreted water are reclaimed before the material leaves the small intestine.
And finally, whatever remains, the indigestible plant fibers, the cellular debris, and a small amount of water, is pushed through the ileocecal valve into the final stage of the disassembly line.
The large intestine.
Right. And the large intestine, or colon, marks a stark shift in priority. The notes are explicit. There is no digestive function in the large intestine.
No enzymes are secreted. The chemical extraction of nutrients is definitively over.
Its primary motor function is to receive this liquid waste, slowly propel it forward, store it as feces, and eventually manage its excretion.
It secretes mucus, but purely as a lubricant to ease the passage of the increasingly solid material.
And it becomes solid because the primary absorptive role of the large intestine is the final reclamation of water, sodium, and chloride.
It pulls the remaining moisture out of the indigestible mass, concentrating it, which is essential for conserving the body's total fluid balance.
But the notes drop one final, incredible detail regarding the large intestine. We just established that the gut itself does no digesting here.
Right.
But the text states, bacteria in the colon synthesize vitamin K and a number of B-complex vitamins. The gut literally outsources essential chemical manufacturing to an alien workforce.
The human microbiome is perhaps the most profound example of biological symbiosis. Our genome does not possess the coding to synthesize adequate amounts of vitamin K, which is absolutely critical for blood clotting.
So what do we do?
Instead, we harbor trillions of commensal bacteria in the large intestine. We provide them with a warm anaerobic environment and a steady supply of undigested dietary fiber.
They ferment that fiber for their own energy, and as a byproduct of their metabolism, they synthesize vitamin K and various B vitamins.
And the large intestine then absorbs these bacterially generated vitamins into our bloodstream. We rely on foreign organisms living inside our digestive tract to maintain our fundamental biochemistry.
It is the ultimate collaborative finish to an incredibly violent and complex journey.
If we synthesize the entire scope of this deep dive, we realize that digesting a single meal requires the coordinated effort of multiple physiological domains.
We observe the massive fluid shifts driven by osmotic gradients borrowing plasma to flood the lumen.
We detailed the autonomous electrical rhythms generated by the interstitial cells of Cachal, waiting for the mechanical stretch of food to trigger calcium-driven action potentials.
We mapped the dense neural architecture of the enteric nervous system, utilizing short reflexes to locally manage the ratio of motility to secretion.
And we followed the precise sequence of the disassembly line, from the anticipatory acid production in the stomach, through the massive absorptive surface area of the small intestine, and finally to the symbiotic water reclamation in the colon.
It is an absolute triumph of biological engineering running silently in the background of our lives.
It really demands a reconsideration of what we consider autonomous. We casually use the phrase a gut feeling to describe an instinct or intuition.
Right.
But having explored the physiological reality of the enteric nervous system, consider the literal, highly sophisticated brain operating inside your abdomen right now.
Just doing its thing.
It is sensing chemical gradients, measuring tissue tension, interpreting osmolarity, and executing millions of precise, coordinated motor and secretory commands every minute.
Entirely outside the realm of your conscious perception.
It forces a deeply philosophical question. How much of our daily functioning is truly directed by our conscious self? And how much is simply the magnificent automated biology we are built upon?
A localized, hyper-intelligent control system managing the chemical breakdown of the external world right inside the hollow tube of your body. Incredible. Thank you for joining us on this deep dive into the gastrointestinal tract. We'll catch you on the next one.